All right, last video on classification. In this video, I want to show you about how to visualize a classifier, get some intuition for what it's doing. And I'm going to show you that by showing you about decision boundaries. The idea here is to look at a way to get an intuition for what the classifier is doing. Of course, if we consider running the classification on any input, if you were to change the attributes, that might change the prediction the classifier makes. So you could imagine plotting what prediction the classifier makes for the entire space of possible inputs. Anytime you have two possible inputs that are very close, very similar, but end up with a different prediction from the classification rule, then we consider them to lie right on or near a decision boundary. So the decision boundary is a location where if you made a tiny change to the input, it would flip the classification from benign to malignant or malignant to benign. So a helpful visualization is to plot these decision boundaries and plot what prediction the classifier would make for all the possible inputs the classifier could face. And then that will give you a way to visualize what's happening. So we're going to do that for an example or two. And the goal here is to help you maybe get a little bit better intuition for what the nearest neighbor classifier is doing by looking at pictures. And I want to work with, first with a simpler example. So I'm going to take a step aside from this breast cancer example, and I'm going to go back to the chronic kidney disease diagnosis example that we had looked at earlier. As a reminder there, that was predicting from blood test results whether or not this person has chronic kidney disease. And here's an example scatter plot to show you what would happen if we decided to use just two blood tests, just the hemoglobin level and the glucose level, and try to build a classifier, a nearest neighbor classifier, using just those two blood test results. That would be great if patients only had to get two blood tests done, not a whole bunch of a dozen of them. Well, here's what the data looks like in a scatter plot. All the healthy patients were in this blue clump in the lower right, and the yellow dots scattered all around are the sick patients from the historical data. And if you imagine this red dot here being a new patient that we want to make a diagnosis of, how would the nearest neighbor classifier do that? Well, it would find the nearest neighbor in the training set. Find the most similar historical patient. So, take a look at this plot for a second. I've got my pointer right on top of the red dot. I want you to see if you can figure out which point be closest, most similar, and then tell me what class you think the classifier is gonna predict. Pause your video and figure it out. Okay. We're back. So let's find the answer, and I wrote some code to compute the answer for me. So here's the code that's gonna show me that red dot, but also find the closest nearest neighbor and draw me a little line to it. So for the big reveal, here is the correct answer. Ta-da! How many of you said the closest point to this red point is that yellow one way over to the left of it? Since it's yellow, that means the prediction of the classifier has the disease. Wait, what? Why is the closest point all the way over to the left when you can see there's a yellow one much closer? That doesn't make any sense. That was what I thought when I first ran this code. All right, trick question. Hopefully I got you. I'm guessing many of you predicted the nearest point is right up here, just above the red point. But actually, no, what's showing up here on the screen is correct. If you said that little yellow one just above it, you were wrong. The correct answer for the nearest point is actually all the way over here to the left. Why is that? Well, the nearest point is the one where the distance is the smallest. But remember how we compute the distance. The distance is like the square root of the sum of the squares of the differences of their attributes. So it isn't necessarily what it looks like on this picture. It isn't necessarily the length of this line. If you see what's happening here, the distance here between these two, well, it's just a difference in hemoglobin level. The glucose level is almost identical, and it's a difference in hemoglobin level of just about, I don't know, 11 to 13, about 2. So that's a very small distance of 2. If you went up to that yellow one that looks really nearby, just a little bit above it, well, you'd end up with a difference in glucose level of probably 20 or 30, which is way larger than 2. So, now maybe you can see what's happening here. The x-axis is on a different scale than the y-axis. And because these numbers here on the y-axis are much bigger, what visually looks like a very small difference vertically actually turns into a very large number. And that distance becomes very large. So, our notion of smallest distance corresponding to most similar ain't looking so good in this example, is it? It looks like it's kind of distorted. So the problem here, the reason why there's a mismatch between smallest distance and our intuition between what we think most similar should be, is because there's difference in the scale of the numbers on the y-axis and the x-axis. The variability on the x-axis is very small. The variability on the y-axis is very large. So you can fix this problem if you first take these numbers and standardize them to put them in standard units. And it turns out that that's often a very good idea when you're using a nearest neighbor classifier, that first you should standardize the units of all your attributes so that you're computing distances on the standardized units. So let's see what happens. I did that. I took the data, converted to standardized units, and now the scatter plot looks like this. It looks the same. Visually, it looks almost the same, but the numbers are different. Instead of the numbers going from, 100 to 500, now the numbers go from like -1 or 0 to 5 on the y-axis. So you can see now the variability on the x-axis and the variability on the y-axis are about the same. And now if we ask the code to find the point that is closest to the red dot, the distance is the smallest, then we get the expected answer of that yellow dot that's a little bit above it. Much better. Okay, so now I'm happy. I've standardized the units. My distance computation corresponds to something reasonable. It's a reasonable way to identify the most similar patient. And we can see here that this red dot is going to get classified as disease by the prediction rule. Okay. Sorry for the long tangent. Turns out this is important in practice. I thought it was good for you to see how this crops up. So now we can get back to the main point I was going after, which is this is a little bit of a visualization that shows you how the nearest neighbor classifier works to classify a new patient whose attributes at the location of this red dot. It finds the nearest point and uses that as the class, the predicted class. So now I can move around this red dot a little bit to help me explore my intuition and see how the prediction would change as I move the red dot, meaning I imagine that this new patient got slightly different blood test results. If I move the red dot down a little bit, then what happens is the nearest point is now different. The nearest point is one over there to the left. But the prediction is still the same. We still predict disease. Now let's see what happens if I move the red dot down a little bit more. What if the patient's glucose numbers had been even lower? Then, well, if I move the red dot down, no change basically, still the same nearest neighbor. Just got a little further away from that neighbor. What if I move the red dot down a little bit more? Their glucose numbers had been even lower. Then what prediction would I have gotten? Well, if I move it down just a little bit more, then I discover now the nearest neighbor is a healthy patient down below it. And now the classifier would predict healthy. So we can see that there's two locations that are very similar. One is just a little bit higher than the other, where the prediction flips from sick to healthy. All right, so what we found is a point that's right near the decision boundary. We discovered there's a decision boundary right here, where if you're just a little bit above that point, you're classified as sick, and just a little bit below it, you're classified as healthy. And if you're right there, then you're right on the bubble, right in between the two. Okay. So this helps me understand what's going on with my classifier if I can start to find that decision boundary and plot it. So I wrote some code to help me do that. And my code, what my code does, don't bother reading all the code. It just says, let's imagine every possible place where a new patient could be. Every possible blood test result. That's all of these light dots. And let's figure out what the classification rule would, what prediction it would make. And let's color the light dot with a light blue or a light yellow according to what prediction the classifier would make. And this lets you very quickly see. You see that blue region down here. There's this blue region down in the lower right. That's the entire region where the classifier would predict you to be healthy. And then the remaining yellowish region is where the classifier would predict you to be sick. So the decision boundary, I'll draw for you the decision boundary. Decision boundary is the place, the border, the boundary between those two regions. So it looks something like this red line. That's the decision boundary. And the classifier prediction rule basically says if you're on the right and below that red line, then we'll predict you're healthy. And if you're to the left or above that red line, we'll predict you're sick. So this tells me something about the rule, the classification rule that the classifier has learned. Now, if I wanted to draw that red line by hand, I could write some code to implement the prediction based on that, which side of that line you're on. But notice that the nearest neighbor classifier has learned that line that comes out of the nearest neighbor prediction rule. It's not something that's embedded in it or hard-coded in it or anything like that. That's what I get if I use the nearest neighbor classifier with k equals 1. Look only at the nearest neighbor. I could also do classification with k equals 5. Make a classification by looking at the 5 closest neighbors and draw the same chart. And now you can see that the shape of the region's a little different. If I now draw where the decision boundary is, it's in a little bit different place. And you can notice that the decision boundary, one difference here is that the decision boundary with k equals 5 is a little smoother. It doesn't have as many sharp angles. It's closer to a straight line. That is indicating it's a little bit less sensitive to small changes in the blood test results, which in many cases is more realistic. You might expect that really small changes in the blood test results are unlikely to represent any major difference in your likelihood of disease. So a kind of a smoother, straighter line maybe is a little more natural, maybe. Okay, so that's an example of how to visualize what the nearest neighbor classifier is doing for the chronic kidney disease prediction task. Now, I'll come back to the breast cancer task, that the data set from Brittany Wenger that we were doing. That's a little harder to show because that had 8 or 10 attributes. And so if I wanted to draw a picture like this, I would need to show an 8 or 10 dimensional plot. And I don't know how to do that. I only know how to do two-dimensional plots. So what I'll do is I'll imagine that we're working with just two of the attributes. Bland chromatin and single epithelial cell size, and I'll plot the decision boundary we'd get with the breast cancer data set if we used k = 1. And you notice here, wow, this is quite a complicated prediction rule. It's got like a decision boundary that you can see has this very funny shape, like really wiggling all around. And then strange stuff, and then weird stuff where if you're up here, it thinks you might be healthy. And then there's this weird island of benignness over here and another little island, and then one strange island over here. Oh my. If we look at that, when I look at that, I look at these islands and I say, that's really dubious. The idea that if my results come out exactly here, that I'm benign, but if it was a little bit lower, a little bit to the left, a little bit to the right, a little above, or a little below, then it'd be malignant. I don't trust that prediction at all. That seems really suspicious to me, to have this kind of such super sensitivity to the exact value of these values. And I bet what happened is there just happened to be one or two patients in our training set who happened to be benign, even though they were in this region where really malignant is more likely. And so as a new patient, if you happen to align with that weird oddball patient in the training set in just the right way, then you get predicted to be benign. And I don't think it's a very good prediction. I think the better prediction, if you end up in this region over here, is probably malignant. Not a guarantee. There were these two oddballs in the training set that were benign, but I sort of guessed that they were one-offs. They were not representative of a typical case. And so I'd probably want the classifier to be predicting malignant in this area over here. So this indicates one of the downsides of the nearest neighbor classifier with k = 1. If you have a couple of oddballs in your training set, and that can easily happen, there can be these tiny areas, regions, where the classifier is making a prediction that doesn't intuitively seem to make sense. It seems the classifiers become too sensitive to the very specifics of the training set and didn't really generalize well enough to spot the pattern that mostly the upper right should probably be diagnosed as malignant. So now let's compare to what happens if we run that same classifier, but now k = 5. Then we get a different looking decision boundary. And now when I look at this one, I see something that to me feels a lot more reasonable. Now I have a decision boundary that's like this. And in particular, you'll notice that some of those islands disappeared. Now, if we have a patient whose results put them around here, it will still predict them to be malignant, which I think makes sense. Despite that one oddball in the training set, there's plenty of others in the training set that are also very similar and that were all malignant. So I think the best prediction around here is malignant. So in this case, setting a larger value of k smoothed out the decision boundary and gave me a rule that at least intuitively feels more plausible to me. And that's what increasing k does with the nearest neighbor, is it gives you a smoother decision boundary. And if we'd increased k = even further, you would have seen even less of this wiggling around and would have been closer to a straight line. So there's no way to know a priori what the right value of k is. All you can do is see which gives you the best accuracy. But hopefully this gives you some intuition for what the effect of that parameter is and what the nearest neighbor classifier is doing. All right, that's all, folks. That's all we have to teach you in this class about machine learning. You've learned a tremendously powerful technique for machine learning. There are lots of other techniques out there. You can take follow-on classes if you'd like to learn about machine learning. It's one of the great breakthroughs of data science. But but hopefully we've given you a feeling for how it works and enough that you can do some non-trivial prediction and classification tasks yourself.